Well, hello retro computing enthusiasts. Mike here. Welcome back to my channel. And today we're going to continue the process of upgrading the JAZ80 breadboard retro computer here up to what I'm calling level 1. And level 1 is going to be sort of like a minimum usable computer. It'll have eventually, hopefully at the end of this video, a serial I/O port on it that we can connect up a virtual terminal on my laptop to and actually maybe start talking to this thing. So that's the main goal for today. We're starting off more or less where we left off in the last video, where I had gotten the CTC chip working and we're outputting 307.2 kilohertz. Now that's going to go into the SIO chip after I put it in here. And that's going to get divided down by 16 to make our bit rate, which will be 19,200 baud. Now, before we get started with that, I need to clean up a few details from last time. Off camera, I was having a lot of trouble getting the CTC chip to work. On camera, it looked like it was pretty easy, other than a few bonehead wiring mistakes I made, and it took me a while to notice. But no, I had more difficulty than you saw, and it took me a while to figure out what the problem was, okay? I had exactly one CTC chip that worked, even though, I harvest these from e-waste over on my main channel, Omega Geek 64. And I had, about half a dozen Z80 CTC chips. And I'm like, they can't all be bad. I've had really good luck harvesting chips from e-waste for reuse, especially if they're socketed. They usually, just pop them right out and they're good. I only had one that worked. And I went through all of them, plugging them in here, and only one worked. Now, I had a sneaking suspicion about what the problem might be. But then I plugged one in and only channel 1 worked. Channel 0 did not work. And as you recall in the last video, we programmed up channel 0 and channel 1 to both put out the 307.2 kilohertz rate. And the fact that only channel 1 was working on one of them, the light bulb really went off in my head. Okay, here's the problem. We just had a simple RC reset circuit over here. And that's fine for the Z80. The Z80 is happy with an RC reset circuit. That works great. The problem is when you start hanging other accessories off the computer that are on the same reset line as the Z80. Okay? Maybe the Z80 comes out of reset first. Maybe it thinks that, the reset line has gone high enough for me to come out of reset. Well, maybe some of the peripherals are waiting for it to go a little higher before they come out of reset. So then they're not all coming out of reset at the same time. So once I saw that the one chip I had in here where channel 1 was getting programmed and outputting the pulses like it was supposed to, but channel 0 wasn't. Yeah, the light bulb really went off. It's like, okay, the Z80 comes out of reset first and starts issuing commands to the CTC. The commands for channel 0 come through, but the CTC is still in reset, so it ignores them. And then the commands for channel 1 come from the Z80, and well, okay, now the CTC's come out of reset, and it accepts the commands, and it programs itself up, and it starts putting out the bit rate on channel 1. Okay, so I realized at that point I had a reset problem. So I went ahead and designed a whole new reset circuit for the JAZ80. So we've got a new version of the schematic here. This is going to be the A revision of the schematic, and we've got a little bit more complex reset circuit here. I have added another chip. It's a 74LS14 hex Schmidt trigger inverter chip, and I'm using 2 of the 6 inverters on it in the reset circuit, as well as a diode. And I've just attached them to the existing reset circuit, and the output of the second inverter is going to be our master reset line for everything on the board that needs a reset. And this works great. I went back and I retested every single one of the Z80 CTC chips that I harvested from e-waste, and every single one of them worked except for one. This one's bad. Okay, so that's about the normal ratio, you know, 6 to 1. And in fact, I even tried an old style 2.5 megahertz CTC, and even though I'm overclocking it, it worked. So yeah, the whole problem the whole time was the reset circuit. And I'm lucky I had one CTC that would work with the cheap RC reset circuit I had in there. So I'll talk a little bit about how this new reset circuit works and why it's better than what we had before. Alright, so the easiest way to explain this, let's take a look at the schematic here. Okay, so we've got our basic RC circuit here that we started out with. 10K resistor and a 0.1 microfarad capacitor and a switch. Now the way this works is when either the system is powered on or you press the reset button switch here, the capacitor is discharged. Okay, so this line right here goes basically to the ground level. And then as the capacitor slowly charges up through the 10K resistor, this line rises until it gets up eventually to the full 5-volt level. So that was just the simple RC circuit we were working with. And like I said earlier, the Z80 is fine with that. In fact, even in the technical documents on the Z80, it says an RC reset circuit will work just fine. The problem comes in when we've got multiple peripherals that need the reset signal, and they're not all necessarily coming out of reset at the same instant. Some might recognize that the voltage level has risen up enough to come out of reset before others do. And that was the problem I was having before with my CTC chips. Only one of them was coming out of reset at the same time, or maybe a little before the Z80 was. All the rest of them were coming out afterwards. So yes, that's a problem, and it's going to be more of a problem as we hang more peripherals off of the system here. So we needed a better reset circuit. So I did a little research and decided to add in this 74LS14 hex Schmidt trigger inverter IC in there. And that's going to give us 6 inverters with a Schmidt trigger input on them. And what the Schmidt trigger input is, basically it has a lot of hysteresis in it, and it has a certain level where it will transition from low to high or from high to low based on its input. And there's a good distance between those levels. So, you know, as this rises, as the voltage on this capacitor rises, you're going to reach the trip level of this Schmidt trigger. And it's going to change state. And it's going to be a very sharp change. There's not going to be a lot of ambiguity about, well, am I there yet? Am I not there yet? It's just going to be a sharp change in state, okay? But since we've got an inverter here, the output of the inverter is going to be the wrong polarity, so we've got to run it through a second inverter to get what we want. So we want a reset signal that goes low when the button is pressed and then comes back up high after the capacitor charges up to a high enough level for the first inverter to change state, okay? And then the output of this inverter can drive all of the other peripherals on the system that need the reset signal. And they're all going to be getting the reset signal going high at the same time. And they'll all come out of reset at the same time. So this is a much better reset circuit than I had before. Some of you may be wondering what this diode is for. Basically what this diode does is this ensures that when the power goes down, when you turn off the power to the thing and the plus 5-volt level comes down to ground, that this capacitor discharges quickly down to the ground level. So that's what this diode is for. You don't want this capacitor holding on to a charge for a while. It will eventually discharge through this resistor. It will discharge through the input to the gate, but you don't want to have the input to the gate at a higher voltage level than the actual voltage that you are feeding the gate chip. So you want this to come down fairly quickly when the power is removed. So that's what this diode is for. This will allow the capacitor to discharge quickly once the power goes down. So that's the new reset circuit. I think we're going to be a lot happier with that on the JAZ80 than the simple RC circuit. Now that we've got that out of the way, I built it off camera just to keep this video from getting too long, just in case I have some issues getting the SIO chip in here and get it running. So let's get started on that. That was the main goal of this video anyway, was to get the SIO chip in there and get some sort of output from it. So let's get to work on that. Okay, so let's get down to business. Let's get the SIO chip in here. So I am using the Z80 SIO0 chip. Now the SIO chip comes in 3 different flavors. There's the 0, the 1, and the 2. And they're all basically the same chip on the inside. It's just they bring different pins to the outside. And with minor modifications, you could use any one of the 3 in this schematic. Shouldn't be a problem, okay? I'm just going with the SIO0 because it's the one I'm most familiar with. It's in the Teletech System Master, which I have done a lot of work on. I'll put a link to the Teletech System Master playlist in the upper right if you care to check that out sometime. But yeah, so we're going with the SIO0. So that's a good spot for it. We'll put it in there and we'll start wiring it in place. So, talking to the outside world, the SIO needs all 8 data lines, of course. It needs A0 and A1. Read, IO request, M1, reset, and a chip enable line. Plus 5 volts and ground, of course. And I think those are, it also needs the clock input. So we'll get started wiring all that up. So all the signals I need for the SIO are right down here at the CTC. So I can just run wires from the CTC up to the SIO, and I think we'll be good. So let me get started with that. I will start with the 8 data lines, and then probably the address, and then the other control lines. The only other line I need is going to be the enable line, or yeah, the chip enable line, which is going to be coming from over here on this 74LS138 on pin 15. So okay, let me get to wiring, and I won't make you watch that process. We'll just be back when I've got some wires in the board. It's kind of odd how they have these data lines on these 2 chips. So I'm running the data lines from the CTC over to the SIO, and they have them staggered, 4 of them on one side of the chip and 4 on the other. And then over here they have them staggered, 4 on one side of the chip and 4 on the other. But here they've got consecutive numbers on one side and then consecutive numbers on the other side. And here they are. It's just kind of odd the way they have that. They have them alternating on the CTC one side than the other. So I've got like 4 different lengths of wire that I'm using to connect them, because some are on this side of the chip, some are on this side, some are on this side, some are on this side. It's a little bit confusing, but I will get it in the end. Then I'll hook up the address lines. These would be the address lines right here, these 2 blue wires. So those should be easy too. Well, I've got the data, address, and system clock line in so far. I went to put in the plus 5 volts and ground, and they really throw you for a loop. A lot of these Z80 chips, family chips do. They have the power and the ground in kind of strange location. Plus 5 volts is at pin 9, and ground is at 31. So, kind of odd. So, but at least this time, I'm paying attention and not making assumptions. So, get the chip powered correctly. So let's see, what do I still got? I've still got to do chip enable, reset, M1, IO request, and read. I still need to get those hooked up. So keep plugging away. Oh, I also need to get the output of the CTC. And then we've got to get the serial clock coming in here up to channel A at pins 13 and 14. Or we could use channel B for the console. The system, I'm used to using channel B for the console because that's the standard for the system master. But we don't have to follow that standard. We can use channel A for the console. Not a big change. So I will get the serial clock from the CTC run up here to channel A. And we'll work with it. Okay, so got some more wiring to do. But we're coming along. Be ready to test in a little while. Okay, so I've got it all wired up. Except for the outputs. They're not going anywhere so far. Okay. So what I want to do now is just power it up and make sure I haven't broken anything. Let's make sure it's still working the way it was before I started wiring this chip in. So let's power it up, press the reset button, and okay, so we're getting pulses out of the CTC again. Let me make sure that they are coming up here to channel A like I want them to. Okay. So channel A is getting the pulses input the way I want them to. Okay. So now what we need to do is we need to write some more code so that we can initialize the SIO and see if we can get something out of it. So let's go do that. Okay, let's take a look at some code I have written to initialize the SIO and send some data out of it. And we'll see if we can get it to work. Up here at the top of the program, we've got some of the stuff you've seen before, like in the last video, we had the diagnostic port up here defined, and we had the CTC ports defined. We're also going to be opening we're also going to be using a stack in this program because we're going to be calling subroutines, and to call and return from subroutines you need a stack. So we're gonna define where the stack location is. I'm calling it 0, but of course the first thing the computer does when you send something to the stack is decrement the stack pointer. So the first position will be FFFF, not 000. So just, for anyone who's confused by that. We've got the CTC divider info down here. But here's something new. We have the SIO addresses defined over here with these equates. SIO A data, SIO B data, SIO A control, and SIO B control. So each port, the A and B port on the SIO, has a data port and a control port. So we define those addresses right here so that we can send the info we need to the SIO to set it up. Of course, the org is 0000 as usual. And then we're going to skip over the init section and the rest of this for now because it calls a lot of procedures that you haven't seen yet. So let's go down and look at those procedures before we talk about what goes on here. Well, there's a CTC init. We've seen that before. This is exactly what we had in the last program, in the last episode, where we set up the CTC to get the bit rates out that we wanted. Okay. So here's the first new code, SIO init. This is going to initialize an SIO channel. So we have 2 channels. And rather than duplicating the code twice, basically we've just created a procedure here that we can call, and we can put the address of the command register for the SIO channel we want to initialize in the C register of the Z80 before we call this code right here, before we call SIO init. And so we have 2 registers, so we can call this twice if we want to set up 2 channels. In fact, if we had a big computer system that had a dozen different SIOs in it, we could call this over and over and over and over again and set up each SIO channel on all the chips to however we needed it. And this is just to save code. I mean, there's no need to duplicate code if you can just, write a subroutine and call it, okay? So the first thing this subroutine does is we load 18 hex into the A register, and we output it to the control register. In this case, we are going to be setting up channel A on the SIO. We'll get to that in a minute. But trust me, we're going to be setting up channel A, so we're going to load 18 hex into the A register of the Z80, and then we're going to output it to the address of the control register of channel A, which will be in the C register of the Z80. Output it, and what 18 hex does is reset the channel. You got to do that first. Next, we're going to write to register 4. And the way the SIO works here is you write the address of the internal register you want to write to out first to the control register, and then the data you want in that register comes next. It's kind of similar to the way we did the CTC, where you would write a command and then the data would follow. It's the same here. We're going to write a command and then the data that we want in that register will follow. So next we want to write to register 4. So we're going to load A with 4, and we're going to output that to the command register, or to the control register, and next we're going to write 44 hex out to that same register. So what this is going to do is this is going to tell us we want to divide the incoming clock by 16. We want 1 stop bit and no parity on our data that's going out. So that's what 44 is going to give us. And you can look this up in the SIO data book if you like. It tells you what all these different registers are, and there's all kinds of different options. So yeah, there's all kinds of different options. You can you don't have to set it up exactly like I have it here, but if you need something different, I'll leave that as an exercise for the viewer to change things. Okay. Next, we want to write to register 5, so we'll output a 5 hex to the control register. And next, we want to write out 68 hex, and this is going to turn on the transmitter. Enable transmission, 8 bits per character. So that's what that's going to do. Next, we want to write to register 3. So we're going to output a 3, and then we're going to output C1 hex. Enable the receive register for 8 bits. Auto enable off, receive on. Turn on the receive channel. So that's what all this stuff does. And this should be all we need to set up the SIO to transmit and receive data between the JAZ80 and a terminal or virtual terminal on my laptop. So let's see here. I've also created a subroutine called putChar. And what it does is it outputs a character in the A register of the Z80 to the console, which would be the terminal on the SIO's A port. So basically anything in the A register on the Z80 will be sent out to the terminal when you call putChar. So the first thing we need to do is we need to save the data in the A register because we're going to change it here. So we're going to push that onto the stack. Next, we're going to read the status of the port A on the SIO. We have to make sure that it is ready to receive a character to send. If it's still in the middle of sending the last character, we have to wait. We can't overwrite the last character. So we're gonna read the status of port A, and we're gonna AND it with 4 hex. That will tell us if it's ready to receive another character. If it's not ready, well, the AND operation will result in a 0. And what we need to do is wait. So we'll jump up here to wait, and we'll go and we'll check again. We'll check the status register again. And, if it still results in a 0, we'll just jump up here. We'll just keep this up until the status register says, okay, it's ready to receive another character. Okay. And then when this is no longer 0, we're going to fall through to here. So we'll pop the data from the A register back off the stack, and then we will output it to the SIO a data port. And that data, once it comes in on that port, is going to start getting sent out the transmit bit of the SIO, 1 bit at a time, plus we'll get a stop bit. Okay, so for now we need some data to send out. So I've created another little subroutine here called say hello. And what we're basically doing here is we're going to load the A register with an H, and the assembler here will automatically translate these ASCII characters in quotes to their ASCII codes. It's that smart. So you don't have to look up the actual ASCII code of the character you want to send. You can just put the character in quotes up here. So it's going to load A with the ASCII value for capital H, and then we're going to call putchar, which is up here. We're going to call that. And as soon as it's able, it's going to send, which, well, this is the first character we're sending, so it should be able to do it immediately. It will send that character out the SIO transmit line. And then we're going to come down here. We're going to load A with a lowercase e, and then we're going to call putchar again. And it's probably going to have to sit up here in the loop and wait for a little while until the transmit buffer is empty. And then it will put the e in it and then start transmitting it. Then we come down here and we do the same with the lowercase l, another lowercase l, a lowercase o, a space, an uppercase w, a lowercase o, lowercase r, lowercase l, lowercase d, and an exclamation point. And then we're going to return. So this is how subroutines work. You call them and then you return from them. So that's the subroutines I've written. Let's go up and look at the code that calls them. So we've talked about all this stuff up here. So we're going to come down here to init, initialize important stuff. First thing we're going to do is disable interrupts. We're not actually using interrupts on this design, although in the future we may. Right now we're not. We're going to load the stack pointer with 0000 up here so that we can get the stack going. And then we're going to call ctc init. So the first thing we need to do is this, what we did in the last video, is set up the CTC so it's outputting the bit rates we need, which is 16 times the baud rate we want. So that's going to execute. It's going to call that routine, and then when it returns from that routine, we're going to load A with 1 hex, and we're going to output it to the diagnostic port. Just like we did in the last video, just to sort of ensure that the code has executed that far. I like to do this just as diagnostics, just to make sure that the code executes the way I want it to. If it gets hung up somewhere, stuck in a loop, crashes, whatever, I can see what's on the diagnostic port and see how far the code got. So we're going to load 1H in there, and we're going to output it to the diagnostic port, and the bit 0 on the diagnostic port LED should light up. Next, we're going to load C with the SIOA control register address, which is up here. So we're going to initialize the SIOA control. We're going to initialize port A on the SIO, so we're going to load it with the port A control register address. And then we're going to call SIO init. So it's going to come down here, and it's going to go through all this stuff, and then it's going to return. And once it returns, we should have the SIO initialized and ready to transmit and receive data. And next, we're going to update the diagnostic port again. We're going to load it with 2 hex, and we are going to output that to the diagnostic port. So now the second LED on the diagnostic port should light up, and we'll know that the code got that far. And then next, we're going to call say hello. And we're going to come down here, and it's going to go through all these characters and output them over the SIOA port. And then when it's done, it's going to return. And then it's going to come down here, and it's going to halt. And the halt light should come on. And we will know that the program has executed properly if we have a 2 on the diagnostic port and the halt light is on. And hopefully we will have hello world exclamation point printed on the screen of our terminal. So let's set up and give it a try, see if it actually works. Okay, so what I have done here is I have a USB to serial converter. This is a TTL level serial converter dongle. We're not going to bother with the RS-232 plus and minus 12 volt level shifters on this design. There's really no need for them. So I have the dongle wired into channel A of the SIO. The RX and TX on this are crossed over and going to the RX and TX on this, and we have ground, so we've got a 3-wire connection between the SIO and my computer now. So hopefully if we open up a virtual terminal on this computer and set it up for 19,200 baud and then turn on the machine, hopefully we will see something on the screen. So let me reposition the camera so we can see what happens on the screen, and we'll fire it up. Okay, so let's see if my creation here actually works. Let's get a terminal up. We'll use TerraTerm for this. And I'll zoom in on the screen a little bit so you can see what I'm doing here to set it up. Okay. We're going to go with a serial connection. And my serial dongle is at port 4, COM 4. Okay. And then we need to change the baud rate to 19,200. Everything else is right. 8 bits, no parity, 1 stop bit, flow control none. Okay. So that's right. So let me zoom out. Hopefully you can see everything. So let me turn it on. Hit the reset button. And hey, look at this. Look what happened. Look what happened. Hello world! Exclamation point. It showed up on the terminal. Look at that. If we come down here, hey look, we've got a 2 on the diagnostic port and the halt light is on. So our program ran perfectly. So we are getting data out of our brand shiny new SIO chip over there. Okay, this is going to open up a whole world of possibilities for us now. We've got good communication going on out of the JAZ80. We have some I/O now. So I think in the next video, what we'll do is I think we'll concentrate on getting some more complex firmware into the JAZ80 now that we can actually send and receive stuff from a terminal. I developed a complete monitor for the Teletext System Master, which I'll put a link to that playlist in the upper right if you haven't seen it and care to watch it. I think I'm up to 14 videos on the Teletext System Master. Now, I wrote a whole monitor program for it that includes all kinds of different functions. And also, I've got a big EEPROM here. I could even get Grant Searle's BASIC in there. So I'm thinking in the next video what we'll do is we'll upgrade the firmware on the JAZ80 so that we've got a complete monitor in here and we've got BASIC. Okay, so let's get that done, and then we'll look at further hardware enhancements down the road, because yeah, there's other hardware I want to put on here down the road, but let's make this thing into a useful computer. So we'll do that in the next video. So I hope you found this video a little bit interesting, educational, informative, inspirational. Get out there and build your own computer. Yeah, it's not that hard. It's not rocket science. It's computer science. Completely different. Anyway, if you found this video at all interesting, educational, informative, whatever, give it a like, give it a thumbs up, and subscribe to see my future videos. There'll be more videos in this series, and I'm going to get back to work on hacking the Nabu again soon. I've got some ideas for it. And there'll be other videos coming down the pike. More Teletext System Master and other retro computing videos. So subscribe to see those future videos. Check out my main channel, Omega Geek 64, where I'm scrapping out e-waste to recover the gold and silver from them. And I recover chips I use for my other electronics and computing projects. So check that out. Fascinating stuff going on there. And I will see you in the next video. Thanks a lot for watching this one. Bye.